Time to get started. Thanks for joining. Actually, the agenda says that there are two of us, but my coworker Mikkel unfortunately had to leave a little earlier. So yeah, bear with me. I try to do my best to entertain you in the next 60 minutes with Edge native applications and correlating it to other like popular terms that we had in our industry for the past couple of years. Most prominent, obviously, cloud native. So before we jump into the topic and sort out a couple of like those terms, quick introduction about myself. My name is Thorsten. I work as a cloud advocate with Fermion. We're a small startup actually building the next wave of cloud computing. That's our vision. And to do so, we heavily rely on server-side WebAssembly. Which means we are not just taking the tech and applying it to certain scenarios. We are also proactively helping the industry to specify what WebAssembly is, to specify what the systems interface is, and to implement runtimes in upstream foundations like the Bytecode Alliance. Yeah, the most important thing over here is my mail address. So if you have any question after the conference or you want to, learn more about server-side WebAssembly, don't hesitate. Just shoot me a mail. I'm happy to jump on a Zoom call, on a Teams call, on a Google Meet, on whatever you're using to have a brief discussion about all those topics. All right, so that's sorted out. Let's tackle the elephant in the room, cloud native. So if you ask like 10 people, you get like 15 different definitions of what cloud native is. At some point in my career, I came up with the intention that actually it does not matter where a cloud native application runs or which technology you use. Let's say good candidates for a cloud native application usually address like some of those adjectives that I placed on the slide over here. So they are scalable, resilient, portable, and obviously they are also observable so that we can get insights of what happens with our application if we throw them over the wall into a public cloud, into a private cloud, or even worse, into multiple public clouds. So I was doing cloud native for quite a while. And cloud native is, well, it's compelling, right? But it's also pretty complex. So we as developers, we are facing a lot of burden that we have to tackle on a daily basis, right? We can't just simply focus on solving a particular business requirement. We have to care about way more. And often that way more is defined by surroundings. That could be the cloud vendor of choice. That could be the underlying cloud infrastructure. There could be silly things like, hey, you have to do a multi-architecture Docker image build in order to run not just on your local machine, but also on the target environment. So there are numerous technologies, tools that we had to learn, that we have to keep up with in an ever-changing world where we see new tools and paradigms approaching almost daily, right? So one of the biggest learning is that cloud native does not mean Azure native, right? Taking an application, betting all in on one particular cloud vendor and leveraging that platform to build something is pretty easy. But what if shit hits the fan and you want to take your application and move it to another cloud vendor? Then you're undergoing a huge refactoring and you have to integrate with other paradigms of how the cloud vendor thinks your app should run. And it all boils down to building cloud native applications is really expensive if you do it in an agnostic and a vendor agnostic way. But the idea is nice, right? We can take compute, we can offload it to someone else's computer and have the app being available on hopefully 100%, but usually I see organizations approaching 5 nines or trying to approach 5 nines, which is expensive and time consuming. So cloud native has been around for 10 to 15 maybe years in different shades or different incarnations. But there is another term when it comes to compute, and I think it's important or crucial to understand the distinction of, or to understand those common terms correctly before we leap into what we refer to as edge-native applications. So we have cloud-native, where we leverage things like Kubernetes, that could be managed Kubernetes, that could be your own, to offload like critical day-to-day tasks to the underlying technology. And then there is serverless. So serverless, the term is around since 2014, 2015, something around around that time frame. And back in those days, it was like, okay, there's, for example, AWS Lambda, there are Azure functions, and each of those services or those platforms, they had their own way of how they want you to write code in a serverless way. But actually, I think serverless is more a paradigm how compute is utilized, right? We have some trigger, some event that happens that could be as easy as an incoming HTTP request. And then we have some code. We have our custom code that is executed, and maybe we compute like a response, return that back, and then everything is tiered down. Sounds phenomenal, however, there is a server in serverless, right? So especially with Lambda or Azure functions, if you have ever used them, you may have recognized that there is like that dilemma of a cold start time that like the older ones in the room may know from back in the days where we did ASP.NET on ISS, where, you know, that one person was the sad one in the morning who hit the just-in-time compilation process. So we have, even with serverless technologies and platforms, we still have that cold start time. But there are solutions for that, right? We can simply pay more, and they over-provision, so there's a server always available for us, and we could get like better cold start times. But that's somewhat against like what serverless actually means. So in contrast to cloud-native computing, where we leverage core cloud compute with serverless, the lifespan of our compute unit is usually something around seconds, maybe milliseconds, but very rarely more than minutes, right? So we're seeing a different way of utilizing compute resources. And if we dive a little bit deeper into what serverless means or what players are on that field, right? We have all those terms like edge, functions, cloud, workers. So functions, workers, cloudlets, however you may want to call them, they are interchangeable, right? They just describe the way of having short-lived compute available to do a certain job. Edge and cloud is more or less an addition to that, and that tells you where do you run, right? Edge is obviously also a spectrum. We were talking about that right before the session. So edge could mean different things, right? Edge could mean like the point of presence locations that cloud providers offer, but edge could also mean like far edge, like a small device attached to a machine or to a vehicle that has to do some computation in order to fulfill a need. So that's really important to understand, that there are like many opportunities to run serverless code, and there are different places where you can run them. So our idea is that we can, maybe instead of reinventing the wheel and saying, hey, that was cloud native, that was serverless, we can go even smaller. Maybe we have to consider like where we run our code to achieve more. So all the huge hyperscalers are continuously improving their offerings when it comes to compute, so where we can actually do computation. And a great example of that is, for example, Akamai, because they had like some super great like pictures that I took for this presentation, but I think that those paradigms are applicable for all the hyperscalers. So I bet all of you have seen a map like that, right? Oh, these are our data centers, and by the way, we spend a lot of money in, click this to, dig holes and to add more fiber to the world in order to introduce low latency connectivity between those data centers. So that's pretty like similar to what Microsoft has on their website when it comes to Azure, what AWS has, and what GCP is also offering. But there's one distinction which made like Akamai super appealing for us, which is Akamai is separating their compute locations into three like kinds, right? We have core compute, where we can rent things like virtual machines, where we can have access to massive GPUs to do like those AI things. All those traditional cloud services are available in core regions. So Akamai has 40-something of those core regions. And then we have the so-called distributed compute, where they have like way more data centers across the globe that are closer to the actual user, but still not what we would consider as edge locations. So they are between the point of presence and between the big data centers, right? And again, we have certain ways to do like computation to run our code. But the interesting thing is that we have an edge. And the edge is basically the point of presence, so where our requests enter their network, the distributed network, where we could place things like CDNs to do asset caching or to deliver media with low latency to the actual user. But there's also a functions as a service icon there. So we can use computation there. And this is what we refer to as the cloud continuum or the compute continuum. So our intention is that with the underpinnings that we use with WebAssembly, we can take code, write it once, run it everywhere, and I bet all of you heard that from Java back in those days. But WebAssembly actually fulfills that promise because it can also run in the browser if you want to. But we can run anywhere, right? We can run on ARM, we can run on x64, Windows, Linux, Mac, and so on. But we can also run anywhere on the compute continuum. So we can take workloads and move them without recompiling them from the core layer to the distributed layer, and even we can push them to the edge layer. And there are some interesting scenarios. So I think the most exciting example was that, so with Apple Vision Pro, you have a camera that tracks what's happening around you and that projects those pictures right in front of your eyes. And they need 14 milliseconds from a camera seeing something to projecting it in front of your eyes. So if we send a request to an edge location, we can do the same in 1 millisecond. Which means at some point, it's smarter to offload computation from a device attached to the user. Attached could also be the phone or the laptop. We can push that off to the edge and leverage the compute capabilities there and deliver with even less latency to the user. So this was a little bit of terminology and how we approach that way of maybe we don't have to reinvent the wheel, maybe we have to consider re-architecturing, so moving the bubbles a little bit around, moving the components a little bit around to do certain things in a way smarter, cheaper, and more efficient way. And that's where we came up with a term that's called selective deployments. So the idea is really, and we will look at that in a minute or two, the idea is to build an application, to deploy it, or to decide at deployment time where you want to place or where you want to do the computation. And there's always that, that handover where we as developers, we build software, we distribute it somewhere through, let's say, a OCI registry or via some sort of distribution channel. And then, in the best case, there's another team which is more experienced when it comes to running things, that they take our assets, so what we build as developers, and they deploy it, they run it. So with selective deployments, we can we can establish a clear contract and saying, hey, I as developer, I don't have to care, I don't have to know where the platform engineers decide to run the API, right? Maybe they have to set some configuration values in a different way, but they can take my application, rip it apart, and selectively place components where they make the most sense. So to do so, we have created a developer tool chain or framework called Spin, and we contributed that to the Cloud Native Computing Foundation. So it is an open source project. We are actively maintaining it and collaborating with others from the community. And it's basically giving you a super efficient and unified way how you can build server-side WebAssembly applications, no matter if you use Go, JavaScript, TypeScript, Python, Rust, or other languages. You have only one simple CLI that makes you productive in building those things. And we will dive into how that looks like before we take a look at the real-like application. The interesting thing, again, is WebAssembly, we can run it everywhere. We don't have to recompile, meaning, for example, if you build an API and you deploy it off to your cloud vendor of choice, you usually end up with an x64 machine under the surface that's powering your application. With WebAssembly, you could simply replace x64 by ARM64 and save roughly 30% on compute spending, because ARM64 machines tend to be like 30% cheaper than the x64 counterparts. So there's also that angle is super sweet, that we can lower our CapEx or OpEx spendings when it comes to public cloud computing. Okay, so there are many resources out there to get started with Spin. I think to get a feeling for how that may look like when we build something with Spin, let me quickly. Is that okay in the last row? Yep, cool. So Spin is a CLI, and obviously, depending on your language of choice, you need your language-specific tooling. So if you're a JavaScript developer, you need like Node.js installed on your machine. For Go, we are leveraging TinyGo. Or for Rust, you obviously have to have the Rust compiler installed on your machine. So Spin comes, or gives you, in a nutshell, a super simple workflow. We have a Spin new, which we use to create a new application. So then we can select from different templates. I've installed like a few of them. There are way more, and you can create your own templates if you want to. So let's say we want to roll with Rust, because rewriting everything in Rust is great. So let's do a hello-ndc. We answer some questions of the wizard, which takes your answers and basically creates a skeleton for us. So I can see into hello NDC right now, and let's open this thing up. So depending on the language you've chosen, we try to generate an idiomatic project, right? A JavaScript project should look like and feel like a regular JavaScript project, and Spin takes care of the heavy lifting to take your source code, compile it down to WebAssembly. So the same applies for Rust. So at some point we end up with some Rust code over here. It basically responds to all incoming requests. And my Rust analyzer will be happy in a second. There we go. And I think if we save this one, it needs some time. So this one responds to all incoming requests by simply constructing a new response and sending that back to the callee. Nothing fancy here. So the idea is I do my work, right? I write some code. At some point, I want to move on and try it. So I have to compile down to WebAssembly. No matter which language you choose, it's as simple as doing a Spin build. We end up with a .wasm file, and we can test it. So Spin up runs the app locally. So our approach is to give you a remarkable developer experience to address like those inner loop concerns, right? I want to build something, I want to test something. Oh, it's great, I want to deploy it somewhere. And that should be as easy as possible. So we do it, let's create a new tab over here, and let's go to hello NDC again. And let's curl this local host 3000, right? So we get back hello world, nothing fancy here. We can take a look at how fast it is. Let's hit it 100,000 times. There we go. And within a second, is it 100,000? Yeah. And within a few seconds, we are done. If we look at latency distribution, we can see we are pretty fast in actually doing serverless compute. The interesting thing, what happens over here? For every incoming request, we load the WebAssembly module, instantiate it, do the computation, we tear it down, there's no shared memory, every instance is a cold start. So you can get a sense of how fast it could be. And we are with ease able to take applications like this, well, applications that actually do something, and deploy them in different places and have like millions of concurrent executions per second without recognizing a heavy load on the machine. So the application, with optimization, we may end up with roughly 40 kilobytes in size. On idle, we leverage in Kubernetes terms less than 1 milli-CPU, and depending on the language you choose, we leverage between 12 to 20 megabytes of memory. Obviously, if you do like memory-intense compute tasks, then those numbers will go up, but it's pretty efficient by definition. So that's the idea. Well, we have a super efficient development workflow, but taking this into like a more realistic scenario, right, where we build more than, let's say, hello world, we have to figure out, hey, how could we remain, or how could we keep that efficiency and factor in different things like where we want to run our application. Speaking about running those applications, so spin up, the local developer experience is great for giving you a sense of how the app works. But you may want to run them somewhere else than your local machine, right? So we created an open source project called SpinCube. That's a joint effort from Microsoft, SUSE, Liquid Reply, and us, which is also open source, also under the CNCF Cloud Native Computing Foundation. And it's basically allowing you to run those workloads in Kubernetes. So we implemented a containerd shim to make Kubernetes just start a process on the underlying node instead of spawning a container if you deploy an app like that, which has some nice effects. So in Kubernetes, for example, Kubernetes expects a pod at least requiring 3 seconds to start. So you can't set a readiness probe smaller than 3 seconds, or if you do so, it will automatically add 3 seconds under the covers, because it just assumes, hey, to start a container, it takes so long. When running WebAssembly on Kubernetes, we can start in a fraction of a second, and we have computation immediately available. Also allowing us to do actual scale to zero and load-based scaling using technologies like KEDA or horizontal pod autoscaler, because we mimic all the Kubernetes primitives. We don't want to reinvent the wheel, right? We want to meet you where you are, network policies, whatever you're used to use in Kubernetes, you can do so. So SpinCube, that's one way how you could run it. We also have like Fermion Cloud, that's a developer cloud for testing things outside of your machine. And we have a hosted platform called Fermion WASM Functions, where you can run an app in a maybe edge-native way. So we think that we as developers, we should not care where we deploy. So we should not pick a region. So with Fermion WASM Functions, for example, you can say, hey, deploy this app. And within a minute, it's distributed around the globe and available in all the regions, because we think an app should be always available. So we're trying to take away the burden from the developers and to make assumptions that apps are always on, always available, and always responsive. So with selective deployments, right, we saw that I created a hello world, right? In a Spin application, we have that notion of a component. So with Spin 3.0, we introduced selective deployments, which allowed us at deployment time to decide, I want to run this on my Kubernetes that maybe, let's say this is an AKS, but I only want to run 3 out of 5 components. The other 2 components are meant to be pushed closer to the user because I want to guarantee low latency. So for example, the front end or a edge-centric API that integrates caching or adds caching to the application to accelerate content delivery even more. Okay, so that said, we could rip apps apart, we can deploy them selectively, but, and I think that's the difference, we code it as one, but we run it or deploy it as many, meaning we are still able to do a spin up to run everything on our machine seamlessly, hot reloading through all the components, no matter which language you use, recompiling on the fly, giving you fast feedback cycles. But if you hit that point and say, hey, now I want to deploy, you can just say these parts over there and the other parts over here. And there are different shades of how you could do that. Maybe you have a Kubernetes fleet where you have multiple clusters, or maybe just a single cluster, and you want to distribute your application into different namespaces. That's one way of doing that. Or another way of doing that is we could have a Kubernetes cluster, a small cluster in the edge, run a subset of the application there, and run another subset of the application at the core compute layer where you have your beefy AKS, LKE, whatever, however Kubernetes or whichever Kubernetes distribution you're using. Okay, that leads us into the actual demo. And let's start by looking at this folder. And maybe I have to decrease the font size a little. So let's open this up. And as you can see, there are multiple folders. So I have one project representing my application. It consists of a couple of back-end API components. I think this one is written in Rust, yeah. This one's written in Go. I have a front end that's written in Vue.js with TypeScript. Yeah, so I can mix and match. I can use those languages that help me to solve a problem in the most efficient way. But still, all I have to do is do a spin build and a spin up to run it on my local machine. If we look at the application manifest, we see that there are many triggers and many notions of a component, right? And those are the boundaries where I can decide, hey, this component should run over there, and that component should run over here. Obviously, you see that there are like endpoints passed into backend components over here. The main reason for doing that is just to create a proper course configuration and not allow calls from any origin, so that only my front end is able to call into the APIs and other origins are blocked. That's why I wired it up in this way. So I have this notion of an application that I can simply go there and do a spin build. So there's spin B, which is basically spin build, that iterates through all your components and does whatever's required to turn that particular language down to WebAssembly. So it takes some time, yep, done. Okay. And then I can do a simple spin up. Oh, nope, it's running, sorry. Oh, the Hello NDC is running on port 3000. So I can do a spin up. And now I see that all the components are running on that listener that has been acquired by the runtime. So the spin CLI spawns the listener. And it just waits for incoming requests. And depending on the request circumstances, it basically invokes or instantiates either one of those components. Okay, let's have a look what I built. So it is localhost 3000. Yep. So I created a simple block, right, that has a front end, that has a back end for doing persistence for the blog posts. We can click around over here, and we have a QR component that's on the fly regenerating a QR code for whatever URL we're currently looking at. Nothing fancy, because I think it does not actually matter what the app does, it's more about the concept. So I can run that on my machine. I can run that on Kubernetes. So I have an AKS cluster with, as you can see, that's roughly a day old. So I installed like SpinCube on it, which has a requirement that we have Cert Manager installed, and KWASM, which allows Kubernetes to run WebAssembly modules on the underlying node. Ingress is installed. That's because I wanted to expose the API, right? And I decided to use WallKey as a persistence layer for my blog posts. So when I run on my local machine, Spin takes care of that. It does not start a WallKey or Redis on your machine. It just says, hey, for development experience, it's okay to use a SQLite as key value store, right? And if you deploy to a real target, you can decide, hey, I want to leverage, let's say, Azure Cosmos DB. I want to leverage a WallKey that I manage or that my team manages. So I have those flexibility to integrate with whatever I'm allowed to use. All right. So spin up the local experience is very easy. We have a Kubernetes cluster with the SpinCube operator deployed to it. And I said that we tried to reuse the Kubernetes primitives that we all know and use for a decade right now. So once you have SpinCube installed on your cluster, you end up with a new CRD called a Spin app. And if we look at, where's my hello NDC? It's over here. So I can say SpinCube scaffold, let's say from ttl.sh hello-ndc 0.1.0. So I can scaffold a manifest, and if I don't save it to a file, it's just printed to standard out. And this is how you could ask Kubernetes to run your Spin application. Obviously, there are more configuration variants on that spec defined. But the idea is that our story ends over here, right? We don't want to tell you, hey, you have to use GitOps, or you have to use Helm, or you have to use a certain way how to get those things into your cluster, right? Those answers are usually, or those questions are usually answered already within your organization. So it works with whatever you're used to use for deploying workloads to Kubernetes. So I'm referring to TTLSH over here, which is an ephemeral and anonymous OCI registry, because we decided that the entire industry is relying on the shoulders of OCI registries, and they are more than just a storage for Docker images. So it's more like a general purpose artifact storage these days. And you're also able to distribute Spin apps as OCI artifacts. To do so, all you have to do is do a Spin OCI push ttl.sh ndc-hello, and let's say this one should remain available for 1 hour. Okay, upload takes the time. So the OCI artifact that I'm right now uploading consists just of your application manifest and the WASM file. There's no container or something involved here. So now that I have this repository or this OCI reference up there, I can go ahead again and say spin cube scaffold hello NDC, but that's for 1 hour right now. Oh, and it's NDC hello. Naming things is hard, isn't it? So there we go. This could be like the representation of my Kubernetes manifest. So let's go ahead and pipe this to kubectl, apply from file, but from standard in, and we see Kubernetes responds back with, hello NDC has been created. So let's have a look. Get spin app, right? So we see there's a backend deployed already, and there's my hello NDC. I asked for 2 instances. There are two instances. Okay. Under the covers, we have an operator in Kubernetes which starts deployment. So there's a hello NDC deployment. There are 2 pods, as you may already experience. Or let me clean up this and do it again. So there are 2 pods, one restarted for whatever reason, which are 40 seconds old, right? So if we get po ndc hello v over here, output as YAML, and if we scroll through that, maybe I should have grabbed it instead. That's smarter. Come on. Let me do this, and grab for runtime. There's a runtime class name, and that's basically the mechanism in Kubernetes that we use to instruct the scheduler, hey, please don't start a container, please go and start a sub-process on that particular node. So right now, let's check how old the pods are again. Okay, I should have talked 18 seconds slower, because that's usually the time that the metric server needs to collect the metrics from the pods to tell us the resource utilization, which should be over by now. So we can say top pod, and we can see that we are right now averaging on 2 milli CPUs and 17 megabytes of memory for the app just to idle around, which demonstrates how many apps you could run on your Kubernetes cluster. So the first limit you will hit is the max number of pods that the cloud vendor allows you to run on your machine. And the second number that you will hit with ease is IP address exhaustion, before you have to think about things like running out of memory, running out of CPU. Okay, let's do a k-edit spin app. What was it? NDC hello. So this is the spin manifest. I can, or the Kubernetes manifest of the spin app. Let's say I want to have 20 instances of that. WQ all how to quit win. And let's say get pod over here again. And as you can see, within a second, we should be, one is crashed back off, why? It should get in a reliable state within a few seconds. But actually, I don't know how many. Give me a sec. Maybe I'm not allowed to run that many apps, that many pods. Maybe 20 was too much for my Kubernetes. No, it's getting there. It's getting there. But within a few seconds, I'm up to have like, 20 replicas of my application, so I can easily scale in and scale out dynamically depending on actual load, and still maintaining a great resource footprint. Okay, so this is Kubernetes, right? And we saw spin up before that. I think that's in 1. No, was it in 2? No, it wasn't 1. Okay, so spin up, we saw that, right? And we see, for example, there's API. So I can do things like spin up, but only the component API. And now you can see that's only launching the API component. So requests to other routes won't be responded. And I can do the same when deploying the app to Kubernetes. So if I go into my all, the image name is not set over here. But as you can see, there's the spec says, hey, use this image. I want to have 1 instance, use container dshim for spin to run this thing, and I configure Redis. I could, however, say on this particular Kubernetes, I just want to run the API, the seed API to, add those sample data into the database, and the API for QR code generation. Everything else is not the business of this Kubernetes cluster. I specify the front, so the actual flow is deploy the front end first and then specify the URL to have proper cores. But I think you get the point, right? I have some configuration that links my APIs to the underlying wall key that's running in my Kubernetes cluster. So I can integrate, I can use secrets and or config maps, whatever Kubernetes has to offer. Okay, so let's do that. Let's go there. Let me grab this ID. No, I don't need the ID. So we can do a kubectl apply from file backend, right? Which basically reconfigures, so it's unchanged. Okay, that's great. So that would actually deploy the workload to Kubernetes. We can wipe it. Come on. Okay, delete spin app. What was it? Backend. There you go. So we have okay, delete spin app, NDC hello. There we go. And let's do a get PO. So we should have no pods running there. Okay. So we do k apply from f backend. Okay. It goes there, fetches the OCI artifact that has all the components in it. Still, we're talking about like up to 10 megabytes for this application because like there's JavaScript in it and there's stuff like in it, right? We need some sort of runtime being compiled onto WebAssembly. So Kubernetes has all the WASM modules. However, I told him to only run API, seed, and QR. So it picks only those WASM modules from the OCI, those OCI layers, and spawns them as processes. So the other two components, front-end and front-end API, those are meant to be pushed far to the edge. So in that terminology that I use right now, it is like the edge compute layer that I want to leverage in Akamai Cloud. And there are different ways or different opportunities. We could leverage like a small LKE Kubernetes cluster that's closer to the user again, and then the workflow would be pretty much the same. But then I would have to care about acquiring a public domain name, wiring things up, And for the sake of simplicity, I decided, hey, I want to have the rest of the application to be hosted on Fermi and WASM functions, like that full-fledged serverless runtime. So all I have to do is to do a spin, let me quickly get a spin akka apps list grab edge. Because I already, I called it NDC, I think. NDC CPH, okay, so then I have to say, because I did that already and wired up the domain name, give me a sec, app, spin, akka, apps, link, app, I think it's app name. Forgot the name, NDC, come on. NDC-CP, almost. Okay. So I did that because in advance of the session I deployed it, and hopefully demo gods are happy with me going off script a little bit. So what I can do a simple spin akka app or spin akka deploy. There you go. There's deploying a new version. Yes, go ahead. So this takes roughly a minute. It uploads the OCI artifact to the service, and the service distributes it around the globe, and it waits for all the health checks to come back successfully, and then it reports, hey, your app is globally available. And I think I broke it. I know that I broke it because I forgot to specify the variables that I wanted to override, but I didn't override them. So let's wait for it to come back, and then we see that it's, it won't work because I did not tell it to point to our Kubernetes, right? So basically it right now deploys everything. Sorry for that. So let's clean up this thing again, and let's say var, I think that's this. Yeah. Okay, unfortunately we have to wait another minute. So what we end up with is, I did not configure an SSL certificate. Sorry for that, but what we end up with is data from Kubernetes being exposed at 131.189.177.188. So that's the external IP address of my Nginx ingress controller. And if we do a get eng svc ep, so to get the ingress, the service, and the endpoints, we can see that I catch everything on that IP address, forward it to the backend service, and the backend service is the first endpoint address over here with IP address 109, and if we do a get POOY over here, we can see that's the IP address of the backend that has those three components. So fingers crossed, let's see. Oh, it works, great. So what happens behind the scenes? It does an HTTP call. If we look into, reload, there we go. If we look at posts, we can see the URL, it goes to Kubernetes over here, but still the front end is deployed not from Kubernetes and not reached from there. If we look at the URL, that's running somewhere on our multi-tenant service closer to the user, allowing us to deliver like the website within a few milliseconds without having us to go all around the world. We can prove that by doing the following. We do a simple curl to index.html, and we ask for all the headers and no content. Oh, no content, I said. Is it small s? Whatever. So we can see that we are hitting our endpoint in EU Central, where in contrast, over here, EU Central, we are hitting EU Central, where in contrast the Kubernetes is deployed in East US. So we don't have to go all around the globe, which also simplify. Obviously, there's some caching happening in the client to cache like the posts. We could factor in an edge cache to cache also assets and data close to the actual user, but only in rare circumstances or a recurring user has to go all the way to the backend for addressing like simple requirements. All right. Another opportunity that I did, or I demonstrated that accidentally, so I can do the spin aka deploy without specifying anything, and let's call it edge native. So I deploy a new app. So I take the same application without recompiling it, without configuring like, hey, key value, how it should deal with that, right? I can deploy it to that service and it works. I don't have to do multi-architecture builds. I don't have to, come up with like different shades of binaries, statically linked binaries, because WebAssembly is the platform I compile to. So it's dramatically simplifying the way how I work on a day-to-day basis as a developer, and other people can decide how and where compute should take place. So this takes, again, like 15 seconds, and we should get back another, there we go, URL, and copying that one. Come on, no. There we I'm here. Obviously, this instance has a fresh, a new key value store. In our case, that's fully managed. You don't have to care about that. But there is no data yet, so I could now send a seed request to the seed API of that particular instance, and we should see the post being displayed there. So let's do that. I think seed is as easy as doing a post. Curl X post over here. Yep, there we go. So now it has some data there, and it's all living close to the callee. And that, again, that's, I think, the important thing. I remain on my local machine. I can up it and run it as one, but I deploy it as many. Okay. So that's the idea, that we take an application and we are able to mix and match languages to address like requirements as efficient as possible, but we are not let's say, limited to a certain platform for running things. So I can push components wherever I want them to and still have inter-component communication working as you would expect it. So on Kubernetes, we have a notion of, let's say, or the other way, let's say we have a notion that's called local service chaining. So you build a spin application, as I did, right? And you can call from one to another component. It feels like HTTP, but it has a special URL, right? It has a spin.internal, so component name.spin.internal, which allows us to say, hey, we don't have to do outbound HTTP for that because the component is next to us. So we can directly invoke that WebAssembly component, that sibling component, and if the component is not there, we can do HTTP, we can do gRPC, we can do different things on how to reach that component that is far away. All right, so that's all I got from DemoWise. I think some key takeaways, so I often like to have like some terms that I can throw into Google Perplexity or whatever you're using these days to learn more. So obviously, Spin, if you never saw Spin, that's the developer tool of choice that we created and we use to build server-side WebAssembly applications. WebAssembly and WASI in general is unlocking not just portability, what we saw over here. We briefly touched performance on how fast a Spin app could respond to a HTTP request. But it also enforces strict security because every workload is executed in a sandbox and it does not have access to any external resources. And external resources are things like the local file system, are things like environment variables. So you can really lock down the environment and run untrusted code in a safe way. So that's why I think that's always important. To see WebAssembly as the first technology era where we can, on a server, on a desktop, assign permissions to applications and not to a user. That's why I placed that there. Core compute, it is obviously capable, right? We can rent beefy machines from Azure, from AWS, from all of them, from Akamai, right? But core cloud compute alone is not enough to address low latency concerns where you have to meet like sub 10 millisecond response times, right? You have to start considering moving workloads to the edge to address those requirements. And with WebAssembly, we have a way to do that and remain productive and remain focused on solving what we are meant to solve and not taming the underlying infrastructure. Because I right now took the head of the developer and at some point the head of the, let's say, of the DevOps engineer or of the platform engineer, however it's called in your organization. But you can separate. You have a clean contract where you can separate those roles and have shared or maybe distinct responsibilities. yeah, compute can happen everywhere, and we will see more and more places where we can leverage, for example, WebAssembly. That could be the fridge, that could be the next Vision Pro, whatever, right? So yeah, that's all I got. And with that, I will open it up for questions. Thank you very much for attending, and enjoy the rest of NDC. Questions? If not, we can answer them, or we can take them offline and answer them with a coffee.